Hello everyone, my name is Nima Mirhadi. I'm a fourth year PhD student at the University of Alberta under Dr. Macchiotto's supervision. Thank you very much for giving me this opportunity to share my work with you. The title of my presentation is Hell's Gate, Rockfalls, Weather and Climate Change. In this presentation, I'd like to share the results from a study on a section along the CN's Yale subdivision, which was done to evaluate the changes in the rockfall probabilities with the climate change. The study area is a 32-kilometer section of the railway operated by CN, which is part of the Yale subdivision in the Canadian Cordillera in British Columbia. The study area begins at Milepost 5 west of China Bar and continues south along the Fraser River alongside steep valley walls and cuts and ends near Yale. According to the model historical weather data for the period of 1990 to 2019, the temperatures range from a monthly average low of -3.9 degrees Celsius in January to a monthly average high of 16.8 degrees Celsius in July. A summary of the weather conditions, including the average monthly temperature and precipitation, is provided in Figure 2. This figure shows that an average of approximately 550 mm of precipitation falls from November to the following January, and the average temperature is below 0 degrees Celsius from December to the following February of the next year. CN continuously records the rockfalls along its railway network. The Yale subdivision's rockfall database includes the time, location, and the approximate size of the rock blocks since 1996. The spatial distribution of the recorded rockfalls, which is shown in Figure 3, reveals that 81% of total rockfalls occurred between milepost 5 and 25, and therefore the probability of occurring a rockfall is higher in this section of track. The time distribution of the rockfalls, which is shown in Figure 4, shows two inconsistencies in the frequency of records. The first change in the frequency is observed between the first 2 years and the remaining records. This one is observed and can be seen between 1997 and 1998. The second discrepancy is observed after 2012, when the average annual rockfalls decreases from 37 per year to about 4 events per year. To minimize the bias in our analysis, we used the records between 1998 and 2011. Therefore, the rockfall database used in this study consists of 401 rockfalls between milepost 5 and 25, which were recorded between 1998 and 2011. This chart shows a summary of annual weather data and rockfalls frequency. The annual average precipitation is 1,370 mm with an average of 194 mm in January. This figure also shows that on average 88 freeze-thaw cycles and 37 rockfalls occur every year between 1998 and 2011. Our objective in this study was to develop a methodology to forecast changes in rockfall hazard as a response to climate change. To do so, we created 30-year weather databases using different climate models and used von Mises circular distributions to find the relationship between monthly normalized weather data and rockfalls. To find the relationship between climate and rockfalls, we did a statistical analysis and used von Mises distribution approach on the 13-year weather data from 1990 to 2019. Three von Mises distributions, as shown in this figure, were defined and mixed to find the best fit to the monthly normalized precipitation. Von Mises 1 represents the last peak of precipitation that occurs at the end of fall around November of each year. Von Mises 2 represents the first peak of precipitation that occurs in the middle of winter around January of each year. And von Mises 3 is a uniform distribution which represents a background precipitation of 65 mm per month. To ensure that the defined distributions are well representative of the corresponding weather data, they were combined by applying proper weight and the correlation coefficient between the recorded weather data and the mixture fit was calculated. Part B of this figure shows the monthly adjusted normalized precipitation and the fitted mixture distribution with a correlation coefficient of 0.96. A similar approach was taken for freeze-thaw cycles. Recorded data show that freeze-thaw cycles peak 2 times every year, once at the end of fall in November and once in late winter or early spring in February or March. Therefore, two von Mises distributions, as shown in part A of this figure, were defined and combined to find the best fit to the monthly normalized freeze-thaw cycles. In this figure, von Mises 1 represents the last peak of freeze-thaw cycle that occurs around November of each year. And von Mises 2 represents the first peak of freeze-thaw cycle that occurs around February and March of each year. Part B of this figure shows the monthly adjusted normalized freeze-thaw cycle and the fitted mixture distribution with a correlation coefficient of 0.99. In the next step, I used the distributions shown in the previous slides to find the relationship between climate data and rockfall events. For this purpose, the relative weights shown in Table 1 were applied on the von Mises distributions defined earlier to create a multimodal fit for the rockfall records. This mixture fit, which is shown in Figure 8, with a correlation coefficient of 0.97, shows that precipitation and freeze-thaw cycle are adequate parameters for finding the relationship between climate and rockfall events. The relative weights show that precipitation has the highest role in rockfall occurrences in the study area with 78% of total weight. This is consistent with the general observation that rockfall occurrences are mainly triggered by precipitation events over timescales ranging from minutes to years. And this also shows that any changes in the precipitation patterns may change the rockfall distribution significantly. In the next step, I wanted to see how climate change impacts rockfalls, so I used a combination of different climate models to create a 30-year climate database. And we know that each climate model uses sophisticated mathematical approaches to predict climate conditions, and because each model is unique and uses different model parameters, intermodel differences would be expected. Therefore, it's recommended to use an ensemble of climate models to get a better understanding of how the climate may be in the future. To create the weather database, we identified the 10th and 19th percentiles of the daily values from 24 climate models, and after removing the outliers, the median values were calculated. The daily median values form the ensemble database and are used in calculating the cumulative precipitation and freeze-thaw cycles. This approach was applied to the predicted values considering the RCP 4.5 emission scenario. RCP stands for a representative concentration pathway. The RCPs describe 4 different 21st century pathways of greenhouse gas emissions and atmospheric concentrations, air pollutant emissions, and land use. The Intergovernmental Panel on Climate Change, or IPCC, describes RCP 4.5 as an intermediate scenario that needs intermediate efforts to constrain the emissions. In this study, we selected RCP 4.5 because it is within the probable CO2 emissions in the future and is in line with future fossil fuel productions. In this slide, figures 9 through 11 show how climate changes between 2020 and 2100 for different RCPs. These figures show the fact that precipitation and average temperatures are expected to increase in the study area in all RCP scenarios. Because precipitation and freeze-thaw cycles have the greatest influence on rockfall occurrences, any changes in these triggering factors affect the rockfall probability. These two figures show the normalized monthly precipitation and freeze-thaw cycles for 2 time periods, 2041 to 2070 and 2071 to 2100. Climate predictions show that higher precipitation is expected in November through the following January, which according to the recorded rockfall activity, it is the time period in which most rockfalls occur. Moreover, figure 13 shows that freeze-thaw cycles change substantially over the next decades, with increases in December and January and decreases in November and March, suggesting that the overall duration of the freeze-thaw cycles will be shorter in the future relative to the reference period of 1990 to 2019. To see how climate change affects rockfall distributions, the same approach was taken, and the appropriate warm-misses distributions were defined on the predicted climate data. It should be noted that these new warm-misses distributions are independent of the ones that were considered earlier for the current climatic conditions, and are defined in a way that the mixture fit has the highest correlation coefficient with the predicted values. The mixture fits for the predicted monthly precipitation and freeze-thaw cycles for 2041 to 2070 and 2071 to 2100 are shown in figures 14 and 15 respectively. Finally, to predict the rockfall changes for the next decades, the same relative weights that I showed a few slides back were used on the corresponding warm-misses distributions, which were defined for the predicted climatic data. Figure 16 shows how rockfall distribution may change in the next decades due to climate change. The percentage changes are shown in figure 17. And according to the results for the period of 2041 to 2070, at least 13% more rockfall activity is expected in winter or from December to the following February. The maximum increase in the rockfall events in the period of 2041 to 2070 is predicted to occur in January. Results also show that the increase in the rockfall activity in the period of 2071 to 2100 is greatest in December and reaches 19% relative to the reference period of 1990 to 2019. On the other hand, rockfall predictions indicate less events in some of the months, which could be caused by the expected shorter period in which freeze-thaw cycles occur. Based on the results, it is expected that the number of rockfall events decreases by 24% on average in October, November, March, and April. So in this research, we created different weather databases, and the weather data shows that precipitation and freeze-thaw cycles contribute 78% and 22% respectively to the rockfall events. We also found that 9 to 19% more rockfall is expected in future winters. Rockfalls are expected to decrease in other months, especially in October, November, March, and April. So based on the findings, more accurate rockfall hazard monitoring and risk reduction strategies can be developed in this area. This study also presents a method to quantify changes in rockfall hazard for climate change scenarios, which can be employed by infrastructure authorities to prioritize their monitoring resources for risk mitigation and enhance resiliency along transportation corridors for those periods of time when rockfall hazards are the highest. And at the end, I want to thank CN and RGHRP for making this research possible. And these are the references that I use in this study for those who are interested in reading more about how climate may affect rockfall probabilities. Thank you very much, and I'm more than happy to answer any questions.
I think in the interest of time, we might have time for one or two short questions. Yes, please.
Thank you. That was really interesting. Have you looked at all at what happens if we have more drought conditions? Because this past year in Europe, many of the slopes produced rockfalls at a rate not previously seen because of the drought conditions there. So that's a future potential as well. Is that something you've considered at all in your work? Or?
No, I didn't consider that in my study, but because my study and the previous studies showed that precipitation has a direct relationship with the rockfall, at least in this study area.
Absolutely.
Yeah, so I was doing the same, and I was trying to find the relationship between the amount of precipitation and the rockfall events. But yes, you are right, and maybe because in some months the precipitation will decrease in the future, so maybe that's a potential trigger for increase rockfalls in this study.
It's one of the challenges with trying to forecast from what we know now into futures that we've never seen before. So yeah, great work.
The limitation with this work, of course, is, as you were saying, right? We don't know how the availability of rockfalls is going to change with the changing climate, with regards to weathering rates and all that kind of stuff. Yeah.
Thank you. That's great.
Thanks, Nima. Really great interrogation of the data.
Thank you.
I was just wondering on the freeze-thaw cycle side, how closely did you correlate the rockfall incident with the freeze-thaw cycles? I'm wondering about the damage that's done by deep freeze, especially, and then the delay that would, like rockfall that would be triggered by that, but some delay later.
So in the CN database that we have the date of the recorded data, but we don't have the date of the actual rockfall. So I didn't have that data to compare the freeze-thaw cycle, the time of the freeze-thaw cycle with the actual time of the rockfalls. So I was focused on the total number of rockfalls, the monthly values, and I tried to see if I can find a relationship between the number of rockfalls and the number of freeze-thaw cycles. So yes, if you have or if you had the actual data of the records, we could see if there is any delay between the rockfalls and the freeze-thaw cycle.
Thank you.
Yeah, you know, the frequency of trains there is probably the same date. Right?
Probably pretty close.
Absolutely, yeah. The problem we have is that we have weather stations along the corridor, and how the weather station translates to the actual temperature at that location in the slope, and then the depth of penetration, the actual temperature drop, how long it was there for it to penetrate, it's tough. So Nima has been working. So this one was a statistical analysis that's quote unquote regional.
Yeah.
He's not presenting it today. I think he presented part of that work last year.
Yes.
But he's been working on a site specific where he's actually been looking at what are those weather signatures leading to one of these failure events, and that's for one of Kristen's sites. So yeah, we hope to share that pretty soon.
Great work,
Tim.
Yeah, that was kind of my question. I call them the climate trigger signatures that lead up to larger rockfall, and also smaller ones and all kinds of other things. But in the larger rockfalls, have you done any research on that as in the precursor intense rainstorms that maybe saturated the rock mass? They correspond to, in my research, I guess I found it that corresponded to the larger landslides, like at Jackass Mountain and a few others.
In the database that I have, we only have the approximate size of the rockfalls, and they didn't. So I don't know if the failure mechanism is different in each of. So I only have the number of rockfalls. I have the location of the rockfalls and approximate.
It sounds like I heard that that's what you'll be looking at. I think.
Yeah, CO18.
Yes, for the CO18, yes, we have the actual amount of landslide there. So we do the change detection analysis there, and we have the actual volume of the landslides there. So yes, I'm doing a separate analysis, and we are trying to see if the volume of the rockfalls, volume of the landslides have any relationship with weather conditions, especially the total annual amount of precipitation.
I also apologize for being late. It's a lot.
Thank you, Steven. You know, that's something that puzzles me, because you've seen that on the Jackass Mountain. I saw that in another hard rock slope a few weeks ago. But Nima's case study is actually on highly weathered sedimentary rock, and the signature is very similar. I'm pretty sure the processes are somewhat similar, but also somewhat different, right? Because of the nature of the material. So